Welcome. In the previous lecture, we saw some basic guidelines for design of the separation system, as what kind of system should be used, the gas vapor separation system, the liquid separation system, the basic guidelines that govern the location of the system or type of the process that we use for separation, etc. Finally, we had seen the applicability of distillation and some basic aspects of distillation, as what should be the sequence of separation of a mixture comprising of different or more than 3, 4 or 5 components. In this lecture, we take ahead this theme and deal with the sequencing of distillation column first, and later on we shall see some other aspects of distillation column such as thermal coupling and Pre Fractionator system and so on and so forth. So, we start our lecture with sequencing of distillation column. In the earlier lecture, I told you that for separation of 3 component mixture, we need 2 columns, 2 simple columns, minimum 2 simple columns, and then we can go for either a direct sequence or indirect sequence of separation. So, the simple column are associated with one feed split into 2 products and key components adjacent in the relative volatility and a reboiler and a condenser. So, what is shown on the screen is a 3 component mixture A, B, C, and simple columns are employed. Then the distillation sequence is as shown. First, A being separated from mixture of B and C, and then B and C split in the second column is a direct sequence, in which in this sequence the lightest component is taken off overhead in each column. Then we have an indirect sequence, the mixture ABC being split as AB together and C separate, B being taken off as the bottom product from the first column, the mixture of A and B flows to the next column and then it is split. So, this is an indirect sequence in which the heaviest component is taken off as the bottom product in each column. Mostly there is significant difference in the capital and operating cost of these 2 sequences. If the number of components in the mixture rise, then the complexity of separation also increases. We have then many options or many possible sequences of separation. I have given here typical example in which 5 component mixture is considered. We have 5 components A, B, C, D and E, and for this purpose we can have 14 different sequences as shown. We have A, B, C, D, E being split in complete direct sequence, A being separated from B, C, D, E, then B being separated from C, D, E, then C being separated from D and E, and then D and E being split in the 4th column. In each sequence you will see that 4 columns are required. Then the second sequence is ABCD mixture, A taken off first from BCD, then BCD mixture split into half, BC together being recovered at the top, DE together recovered at the bottom, and then these binary mixtures are further split as BC and DE. Then in the third possible sequence, we have separation of A again from BCD mixture first, and then BCD quaternary mixture is split as BCD together and E being separated, that is indirect sequence, and then we are left with a BCD ternary mixture which is again split in direct and indirect sequence, like B being separated from C and D and C and D being split in the 4th column, or BC being separated from D and the binary mixture BC is split in another column. So, in this way, if you start writing, you can write 14 different sequences as shown in this figure. Heat integration is another issue in this case. We cannot have luxury of providing utilities for the reboiler and bottoms of each of these columns separately. We have to have heat integration. We have to see where surplus heat is being available, and that surplus heat as far as possible should be utilized to meet the energy demands. That way we bring down the operating cost of the process. So, heat integration is an important issue. Heat integration may also affect the operating cost significantly. Heat integration can be achieved within a separation sequence, like columns coupled together, and that is straightforward, that you have vapor at the top of each column and liquid at the bottom of each column. Then you can have coupling of the columns such that the vapor from one column condenses into the reboiler of another column and then drives the reboiler. But to achieve that, you have to have sufficient temperature difference, and you have already learnt the boiling heat transfer in the course NPTEL course of heat transfer. you should always have your reboiler, which is typically kettle type reboiler. It should always operate in the nucleate boiling region. So, you have to have about 40 to 50 degrees centigrade of difference between the condensation temperature of the vapor and the boiling point of the liquid, and now you can achieve that difference by shifting the pressures of the column. You reduce the pressure of the second column, so that the boiler temperature reduces, increase the pressure of the first column such that the condensation temperature increases, and then have the coupling. So, that is heat integration within a sequence. These sequences can also be coupled other streams in the process. Okay. So, when we select a sequence, a best possible sequence, then we have to take into consideration this important aspect. So, it may not be possible that you will have out of this 14, or if you consider 6 component mixture, and there are 64 sequences, or sorry 46 sequences for 6 component mixture, so on and so forth. It is very difficult that you will end up with a single best sequence. You will always end up with certain set of sequences which have more or less similar benefits, okay, or similar operating and capital cost. Okay. So, this point you need to note. However, only let us say least total vapor load or flexibility in heat integration may not be criteria. There are some practical constraints in sequencing, in choosing the best sequence of a distillation column. Okay. The practical constraints are as follows, and these reduce the number of options that can be considered. First is the safety consideration. Hazardous components to be removed from the process as early as possible to minimize inventory of that material. Then if a component is highly reactive or heat sensitive, then it should be removed as early as possible, because as you go ahead, as you go on separating the mixture, the temperature of the column is likely to increase with heavier components left in the stream, and then it is likely that the component which is heat sensitive may get degraded. Then if a component is corrosive, then it should be removed as early as possible to minimize the use of expensive material of construction. Then if a component is likely to decompose in the reboiler and contaminate the product, then it should be removed as early as possible. In such cases, the finished product or final product should not be removed as the bottom product, it should always be removed from the top. Then for compounds which are likely to undergo polymerization during distillation, we have to add certain chemicals like hydroquinones as inhibitor, and these inhibitors tend to accumulate in the bottom of the column. So, they contaminate the product. So, again you cannot withdraw the final product as the bottom product. And in the feed, if you have some components which are difficult to condense, which have low condensation temperature, then they require low temperature refrigeration or high pressure for total condensation. These are basically the light ends. In such situation, the light components should be removed from the top of the first column, so that in the subsequent columns you are left with only the components which condense at temperature higher than about 30-40 degrees centigrade. So, you can use cooling water for their condensation, and no refrigeration or high pressure is required. Okay. So, these are some of the qualitative guidelines for deciding the column sequence or the practical constraints that may occur. There is a very interesting set of heuristics for selection of sequence for non-integrated columns. Means a non-integrated column means each column having its own condenser and own reboiler, which is driven by independent utilities. Okay. So, let us see these heuristics. There are 4 common heuristics. First heuristic says that separation in which relative volatility of key components is close to 1, or components which show azeotropic behavior, should be performed in absence of non-key components. This is what we have already seen earlier. Okay. Or let us say do the most difficult separation last. Then second heuristic says that sequences removing the lightest component alone one by one in the column overhead should be favored, or favor direct sequence. The third heuristic says that a component comprising of large fraction of the feed should be removed first, or in other words, separation with the highest percentage recovery should be done last. In this way, the net amount of liquid that you are handling or net amount of mixture that you are handling will be lesser, and thus the cost of operation will go down. And finally, is the fourth heuristic says that favor near equimolar splits between top and bottom product in individual columns. Okay. Now, these heuristics have been devised on the basis of practical observations, data that has been operation data, log books that have been operated for long time. So, these are merely practical thumb rules. These are not devised on any, let us say, theoretical considerations. Secondly, these heuristics are restricted to simple columns with no heat integration, means all the reboilers and condensers serviced by utilities, as I just said. Then arrangement of sequences should be such that the cost of separation reduces as the separation proceeds, and difficulties arise when the heuristics are in conflict with each other. Like one heuristic will recommend one sequence, another heuristic will recommend another sequence. Okay. So, this kind of situation may arise very frequently. Now, let us see an example to which we shall apply the 4 heuristics that we stated just now. We have, let us say we have a 5 component mixture, so that we have 14 different sequences. The flow rates are given in kilomole per hour, component A 45 kilomole per hour, component B 135 kilomole per hour, C 225, D 175, E 325. E is the heaviest component, so we define the relative volatility with respect to it. D has a relative volatility of 1.5, C 3, B 4 and A 8. So, A is the lightest component with highest relative volatility. The relative volatility between components can be calculated by ratio of their relative volatilities with respect to E. Like for example, the relative volatility of A with respect to B is 8 divided by 4, that is 2. Then relative volatility of B with respect to C is 1.33, 4 divided by 3 and so on and so forth. Now, we apply the heuristics in order of sequence. Heuristic 1 says that do the most difficult separation last. So, now if you look into all these relative volatilities, the relative volatility of B with respect to C is the least, 1.33. So, this heuristic says that do the BC split last, as this separation has smallest relative volatility. Then heuristic 2 says favor direct sequence. So, remove A from 4 components, A being the lightest element. So, that should be removed first. So, the sequence A, B, C, D, E should be favored. Then heuristic 3 says that remove the most plentiful or highest molar component with highest molar flow rate first. So, that component is E. So, the heuristic 3 recommends the split A, B, C, D from E first, and heuristic 4 which states that favor near equimolar splits between top and bottom will recommend A, B, C being separated from D as the first column separation. Okay. So, you can see that 4 heuristics recommend 4 different sequences which are in conflict with each other. Now, what to do in this case? In this case, we have to apply the other constraints based on other practical constraints, etc., or other considerations like how material is corrosive, heat sensitive, so on and so forth. We have to choose any of this sequence, and then reapply the sequences again. So, we start with one decision here, like we say that we favor direct sequence. So, we remove A from the BCD mixture, so that we do not require refrigeration or high pressure in the subsequent columns to condense A. So, after removal of A, we are left with BCD mixture, and then you apply the same sequence of heuristics for BCD mixture and proceed. Again, you will see that these are in conflict with each other. Again, you have to choose based on your other considerations. You have to choose one of the sequence and then apply the 4 heuristics. Now, due to these conflicts, it is difficult to establish a good sequence with these heuristics. Although you can arrive at few good sequences, but it is difficult to devise a single best sequence. So, more skill is needed in application of these heuristics, and they could be ranked in order of importance. However, rank order might change from process to process. That is another thing, depending on components of the process, nature of process. Therefore, we need a more general and quantitative method for deciding between the column sequences. Now, vapor flow rate up the column or vapor flow rate inside the column is a good measure of both capital and operating cost. Higher vapor flow rate means you require a fatter column, okay, and that increases the fixed cost as well as operating cost. Okay. Higher vapor flow rate will also mean higher heat duty at the reboiler. Okay, that means increase in operating cost also. Fatter column due to high vapor flow rate increases capital cost, higher heat duty at reboiler increases operating cost. So, you can assume or you can take the vapor flow rate inside the column as a measure of capital and operating cost, and you have to choose a sequence that has the minimum vapor flow rate. Okay. Now, there are 4 columns in each sequence. So, you have to consider the total vapor flow rate of all 4 columns. Now, how do we determine the vapor flow rate inside a column? We can use the multi-component form of Underwood's equation. These equations I am sure you have dealt with in the course of mass transfer, and so we take these equations directly. We do not go into the derivation of these equations, but you can find them in the very common textbooks like Perry's Handbook or a book by Trebal, these Underwood's equations. Okay. The minimum vapor flow rate in a single column is obtained by alternate use of the following 2 equations. Underwood's equations are a set of 2 equations. First equation, summation I running from 1 to NC, where NC is the total number of components, alpha I into XFI. XFI is the composition of the feed. F stands for feed, I stands for component. Okay. So, XFI is the mole fraction of component I in the feed. So, alpha I into XFI divided by alpha I minus theta is equal to 1 minus Q. Now, Q is the thermal condition or quality of the feed. This aspect also you have dealt with in the course of mass transfer, the quality of the feed. When the feed is saturated liquid or liquid at its bubble point, then value of Q is 0. Oh, sorry, value of Q in that case is 1. If the feed is at its bubble point. Then the second equation is R minimum plus 1 is equal to summation I running from 1 to NC alpha I into XDI divided by alpha I minus theta. D stands for distillate. So, XDI is essentially mole fraction of component I in distillate, and then you have to solve. You have to first obtain value of theta, which is a variable defined by equation 1, and then substitute that in the second equation. Okay. Now, depending on how many components you have, the number of theta values will vary. Okay. To calculate the total vapor flow rate for a single column in sequence, first assume a feed condition such that Q value can be fixed, and as I just said, the most common value of Q is equal to 1, which corresponds to liquid at its saturation point or liquid at its bubble point. This is the case for most of the columns that are designed. Okay. Then equation 1 can be written for all NC components of the feed and solved for values of theta. There will be NC minus 1 real positive values of theta, which will result as the roots of that polynomial which satisfy equation 1, and each of these theta values will lie between the alpha values of different components. This is very important. Okay. Each theta value will lie between the alpha value between of the components. Okay. Now, among different values of theta, the one that lies between alpha values of the light and heavy key is considered. Let us say B is our light key element and D is our heavy key element. So, the one that lies between alpha BE and alpha DE should be considered. Now, once you get this value of theta, substitute it in equation 2 and solve it for R minimum, that is the minimum reflux ratio for a predetermined values of XDI. Depending on the purity level that is desired, you decide values of XDI, okay, the mole fractions of various components in distillate. If the split is sharp, let us say you are splitting between B and C. Okay, if using value of, if you have designed your column with alpha BC, okay, that is ratio of alpha BE and alpha CE. We have defined, usually the relative volatility values are defined with respect to heavy key element. We assume that the heaviest element is the heavy key element. Therefore, all values of alpha are defined with respect to E in a 5 component mixture. So, let us say you are splitting between B and C. If B being your light key element and C being your heavy key element, then you split between B and C and then use value of alpha BC, okay, and you use the value of theta that lies between alpha BE and alpha CE, and on the basis of that, if the split is sharp, then all components heavier than C will not end up in distillate, all components lighter than B will not end up in the bottoms, okay, and then you can decide the values of XDI. Otherwise, you have to calculate the values of XDI depending on the purity or recovery of different components that is there, and once you do this, then you can substitute these values into the second equation. The second equation, R minimum is equal to summation I equal to 1 NC. Now, this equation is an explicit equation. It is not implicit as the first one. You can directly solve it and get the value of R minimum, that is the minimum reflux ratio. There is a thumb rule that the actual reflux ratio should be 1.2 times the minimum reflux ratio. Okay. Reflux ratio is a parameter which determines the total cost of a distillation column. You are going to learn this particular aspect in the course of mass transfer, where you will be taught as how the operating cost and the fixed cost varies with respect to R. If you have a reflux ratio much higher than minimum reflux ratio, you are going to have very less number of plates, okay, very few plates. However, the total amount of liquid that you will be handling will be high, the operating cost will rise, vapor flow rate will be high, the liquid boil rate will be high. Okay, if you reduce R reflux ratio, if you keep it just at R minimum, you require infinite number of plates, so that is out of question. But if you keep it just above R minimum, then you are going to end up with very large number of plates that will increase the total fixed cost of your column. However, the operating cost will be low. So, if you plot these two costs with respect to reflux ratio, somewhere you are going to hit an optimum, and that optimum is usually at 1.2, which means when the actual reflux ratio is 1.2 times the minimum reflux ratio, you have the optimum. Now, using this thumb rule and the R minimum, which is determined from equation 1, you can calculate the vapor flow rate as V is equal to D into 1 plus R, where D is the distillate flow rate, R is the reflux ratio. Okay. Now, distillate flow rate, again you can calculate by overall mass balance depending on the feed composition, recovery, etc. Again, these aspects you are going to learn in the course of mass transfer, so I do not cover it here. Okay. These calculations are explained in course of mass transfer. So, with this you can determine the vapor flow rate of each column, okay, and then you add the total vapor flow rate of 4 columns in each sequence and find out which sequence has the minimum total vapor flow rate. Okay. However, this method is implicit, it is rigorous, okay. It requires iterative calculations, especially to determine the values of theta from the first equation. And then the minimum vapor flow rate is merely a guideline for deciding column sequence. Therefore, we would like to go for some method which is explicit in nature, which can be easily solved using simple calculator. Now, Porter and Momo, these two scientists, invented a method in 1991 which is a simpler form of this Underwood equation, and it is explicit in nature. Now, let us see what the method is. The basic relation between the vapor flow rate V, distillate flow rate D and reflux ratio R is V is equal to D into 1 plus R, as we just saw. Okay. Then we define the ratio of actual to minimum vapor flow as RF, which is equal to R by R minimum, and then we substitute for R as RF into R minimum. So, V becomes equal to D into 1 plus RF by R minimum. R minimum is then calculated from the binary form of Underwood's equation applied between key components. So, R minimum is equal to 1 divided by alpha minus 1 into x d L k divided by x f L k minus alpha into x d h k divided by x f h k. Now, this equation for R minimum is derived by solving simultaneously the equation for operating line in the enrichment section, in the stripping section, and the Q line, the quality line, quality feed line. Okay. Again, this is covered in the course of mass transfer. So, I do not cover it here. When at the minimum reflux ratio, the point of intersection between the stripping section and enrichment section falls on the equilibrium curve. So, assuming Raoult's law, you have the equation for equilibrium curve, that equation plus the equation for operating the enrichment line and the Q line should be solved together to get R minimum. So, that derivation could be found in the book by Trebon. However, that equation is derived for binary mixture. Now, here although we have a multi-component mixture, we assume it to be binary, where the two components are heavy key component and light key component, and that is how the equation for R minimum is obtained. Okay. Alpha is the relative volatility between key components, L k stands for light key, H k stands for heavy key, and X stands for mole fraction in this equation. Now, if we assume sharp separation, as I just mentioned, okay, that if the relative volatilities are sufficiently different, sufficiently large, then you are likely to have a sharp separation, which means in a, let us say, 5 component mixture, if you are splitting between B and C, then only A and B will appear in the distillate and C, D, E will appear in the bottoms. No component heavier than C will appear in distillate, no component lighter than B will appear in the bottoms, that is obvious. So, that is sharp separation, that is overhead product comprising of light key components and components lighter than light key, bottom product comprising of heavy key components and components heavier than heavy key. And if that applies, then XDHK, that is mole fraction of heavy key in distillate, as well as XBLK, that is mole fraction of light key in bottoms, is 0. Moreover, if you assume almost complete recovery of light key element in the feed as distillate, then we can say that F into XFLK, which is the total light key element molar flow rate into the column, F is the total molar flow rate of the mixture, and XFLK is the mole fraction of the light key element in it. So, F into XFLK is the total light key molar flow rate into the column is equal to D into XDLK. XDLK is the mole fraction of light key component in distillate, D is the total distillate flow rate. So, if the recovery is complete, then F into XFLK is equal to D into XDLK. And then for the ratio XDLK divided by XFLK, we can substitute F by D, and that exactly we do. We first substitute XDHK is equal to XBLK is equal to 0, and then XDLK divided by XFLK is equal to F by D, and then R minimum becomes 1 divided by alpha minus 1 into XDLK divided by XFLK, and then is equal to alpha, the same thing simplified further, R minimum is equal to 1 divided by alpha minus 1 into F by D. Okay. And then if you substitute this particular value of R minimum into the expression for vapor flow rate, then we get V is equal to D into 1 plus RF divided by alpha minus 1 into F by D. We can expand this particular expression because we have assumed a sharp separation. That means distillate contains light key and components lighter than light key. Okay. So, you can expand the expression as follows. Okay. V is equal to D, D comprises of Fa plus Fb up to Flk light key element plus Rf into F divided by alpha minus 1, because once you expand this particular expression, then you get D plus Rf into alpha minus 1 into F. Okay. that is how. And feed comprises of all components F A plus F B up to F N C, where N C is the number of components divided by alpha minus 1 into R F. But remember one important thing, that this alpha is alpha between key components. Okay. Alpha is between key components. So, when you apply this particular expression for each column, you have to see carefully as where the column is splitting the feed. So, if the column is separating A, let us say you have a 5 component mixture and the first column separates A from B, C, D, E. So, the split is between A and B, because components heavier than B are all going to end up in the bottom. So, for this alpha you have to use alpha AB, but in the next column let us say BC is being split from DE, as in one of the sequences we saw. Okay. After separation of A from BCDE, we are left with quaternary mixture BCDE, and let us say that quaternary mixture is being split as BC and DE, then you have to use alpha CD, because there the split is between the key elements C and D. So, when you apply this particular expression, you have to be very careful for using the value of alpha. Alpha has to be between the key elements, alpha has to be that alpha between the adjacent elements which are being split in each case. Let us say quaternary mixture is being split as ABC, BCD and E, okay, the indirect sequence. Then you have to use alpha DE, because the split is essentially between D and D. The components later than D are all going to end up in the distillate. So, this expression is very easy to handle. Okay, the only thing you need to know is the flow rate of all components to the column and relative volatilities. So, this is a very handy tool or very simple explicit expression for determination of the vapor flow rate in a single column in terms of the feed to the column. Then you apply this expression for each column in the sequence and then sum up the total vapor flow rate in the sequence. Now, one shortcoming of method of Porter and Momo is that it over predicts the vapor load than that predicted from the full multi-component form of Underwood equation. However, Porter and Momo have demonstrated that the rank order of total vapor load follows the rank order of total cost. Okay? That is proven. Also, although quantitative vapor flow rate predicted by Porter and Momo is higher than Underwood's equation, which is a more rigorous method, it has been demonstrated that the total cost follows the total vapor load. Okay? So, when we are in the process of shortlisting from a very large number of sequences, this method is very useful. Although quantitatively it may not be very accurate, we are only in the screening process. So, in that process we do not bother much about the accuracy, quantitative accuracy, and then we can work with this expression to shortlist, let us say 10 best sequences out of 100, and when these 10 sequences are obtained, we can further distinguish by more rigorous method. Now, we can also have columns with more than 2 products. It is not necessary that each column will have only one product at the top and one product at the bottom. What I have shown here is an interesting case of a ternary mixture being split in single column rather than 2 columns. Separation of 3 component mixture with simple column has 2 possible sequences, direct and indirect sequence. However, under certain circumstances, it is possible to draw more than 2 products from a single column. Now, how? If you have a feed such that the middle component B comprises more than 50% and either of A and C is less than 5%, like case A, which is shown here on the left hand side, is for feed with more than 50% of the middle component and less than 5% of the heavy component, and the case B, which is shown on the right hand side, is feed with more than 50% of the middle component and less than 5% of the light component. In this case, there could be 3 products from the same column. The designs are both feasible and cost effective compared to the single arrangement and standalone basis. That means reboilers and condenser operating on utilities for certain range of conditions. If the feed is dominated by middle product and heaviest product is present in small quantities less than 5%, okay, that was the case A here. In this case, you can go for configuration such that you draw a side product from one of the bottom plates as a vapor side stream. The heavy product goes down the column past the side stream. Unless the heavy product has small flow rate and middle product has large flow rate, a reasonably pure middle product cannot be achieved. The side stream is taken off as a vapor product so as to get the desired purity. So, here what you see is that in the near the bottom plates, okay, C will go down. So, the mole fraction of C will increase very rapidly in the bottommost plate, okay, in the last few plates. And because the feed is dominated by B, if you take plates which are somewhere higher than the bottom plates, somewhere here, let us say among the last 10 plates, somewhere near the bottom, you will see that the mole fraction of B is sufficiently high. It may not be 99.9, but it is sufficiently high, let us say 0.9, 0.92. And if B is not required in that high purity, then you can take off B as a vapor side stream. C is heavier component, so it will be in liquid phase mostly. You take off a vapor side stream and then obtain 3 products from the same column. Now, if the feed is dominated by middle product and light product stream is present in small quantities less than 5%, then arrangement B is a good option. Now, here what is happening? A and B both flow upward, but the composition of vapor in the topmost plates increases very rapidly for A, like the recovery of A is 99.9% and purity is also 99.9. So, if you take the topmost plates, the vapor rising from these plates will be pure, almost pure A. But if you see the liquid near the topmost plates, okay, then liquid may have composition of B sufficiently high, let us say 90%, because the total feed is dominated by it, not because the relative volatility, but since the total feed is dominated by middle product, then in the topmost plates you may have sufficiently high purity or sufficiently high composition of B, so that a side stream can be taken, okay. And then again there will be 3 products from the same column. So, pure side product is achieved if light product has small flow rate and the middle product has high flow rate. The side product is taken off as a liquid stream to obtain reasonable purity. If you take the topmost plates, then B being heavy component, it will be mostly in the liquid phase. So, vapors rising will have most of A, the liquid that is there will have sufficiently large quantity or mole fraction of B, so as to obtain a side stream. So, in summary, single column side stream arrangements are attractive when middle product is in excess and one of the other components, either light or heavy component, is present in minor quantities. So, in this way you can reduce the operating cost. Remember again that a side stream may not have very high purity, but in many cases the side stream is recycled to the reactor. Okay. So, in that case the purity is not a very big constraint. Then let us consider another arrangement called Pre Fractionator. Okay. Consider 3 product separation as shown below, in which the light and heaviest components are chosen to be the key separation in the first column. Okay. So, the first column, it splits the ABC mixture not very sharply, but A and some B and C and some B, like this. The A and C mostly end up in top and bottom, but B gets distributed, and then the mixtures AB are split in another column, BC is split in another column. So, totally you require 3 columns. The first column may not have very large number of plates because it is not going for sharp separation. Okay. So, few plates just to separate the components, the ternary 3 components AB and BC, B getting distributed between the 2 streams, and then you have individual splits. So, you have basically 3 columns here. Now, these columns can be coupled, okay, especially the next 2 columns, as you will see that the bottom and overhead product of the second and third column is same, that is B. Okay. okay, and both is pure B. So, you can couple these two columns, and that coupling gives what is known as a Pre Fractionator. In Pre Fractionator, the ternary mixture ABC is split into two parts, a small column with a partial condenser and a partial reboiler, and then a tall column in which A is taken off as the top product, B as the middle product, and C is the bottom product. Okay. So, from the previous arrangement, we are simply connecting the second and third column to obtain B as a side stream, and this arrangement is called Pre Fractionator. Remember that Pre Fractionator has a partial condenser and partial reboiler. These Pre Fractionators are reported to save about 30% of the energy than the conventional arrangement for the same duty. The reason underlying this is that the Pre Fractionator arrangement is fundamentally thermodynamically more efficient than the simple arrangement as described earlier. Now, let us elaborate on this particular thing, how it is thermodynamically more efficient. In the first sequence, we were splitting, let us say, A from BC, and then B was being further split into B, and the mixture BC was being split into B and C. Now, this is the composition profile for the two columns. We have column 1, we are plotting mole fraction of B against the column height. Okay. So, in column 1, the mole fraction of B is almost 0, okay, because A is being obtained as a pure product. However, B ends up in the bottom. So, the bottom of column 1 has sufficiently large concentration of B. Now, this becomes the feed to the next column, and then again in the second column, the B component is obtained as a top product with sufficiently high purity, and C is obtained as the bottom product with high purity. So, the mole fraction of B in the bottom product of second column is close to 0. Now, in this sequence, the composition of component B in the first column increases below the feed as more volatile component A decreases. However, moving further down the column, the composition of component B decreases again as the composition of less volatile C increases. So, if you couple the columns, okay, if you let us say if you are considering this as a single entity, you obtain here a maxima for B, and then again B is getting remixed into the process. The first column separates A from BC. So, B flows down, its concentration increases. In the second column, B flows up, and then again its concentration decreases. So, in between you are going to have a maxima for B. So, the composition of B reaches a peak only to be remixed, okay, and this remixing in simple distillation column is the source of inefficiency of separation. In a Pre Fractionator, this particular deficiency is removed. Now, let us see what happens in a Pre Fractionator. In a Pre Fractionator, the ABC mixture is split into mixture of AB and BC, and this mixture is of course, here we have a partial condenser and partial reboiler. We do not have total condenser, total reboiler. We have a partial condenser and partial reboiler. This mixture of AB and BC is fed at two locations in the main column. In the Pre Fractionator system, we are coupling the two columns that were there. Now, what happens here? If you see the concentration profile, the mole fraction of B being plotted as the column height. In the first column, you get a distribution of B. B does not get sharply separated, B gets distributed between the top and bottom product. So, in both cases, you have sufficiently large mole fraction of B column at the top as well as at the bottom. And then after being fed into the main column, as you go to the top of the column. So, this is the feed, Pre Fractionator top feed. Here you see that concentration of B decreases as you go to the top because A becomes more and more pure. So, B flows down. If you see bottom part, then again concentration of B decreases because B flows down, C flows down as the purity of C increases and A flows up. So, somewhere in the middle section of the main column, the concentration of B reaches very high, let us say 0.9, 0.92 close to 1, and then B is taken off as a side stream. So, in this particular case B is not remixed as the earlier case. In both sections of the main column, remove only one component from the product of that column section, and this is also true for main column. Thus, the remixing effect of simple column sequence is avoided, okay, and that helps in increase of the efficiency. Another feature of pre-fractionator is that it helps in reducing the mixing effect. Losses occur in the distillation operation due to mismatches between composition of the column feed and the composition of the feed tray. But here the feed is being split into two parts, one part which is richer in A, one part which is richer in C, and then these are coupled to the main column. So, as pre-fractionator distributes component B between top and bottom, greater flexibility is achieved to match the feed composition with one of the trays in the column to reduce the mixing losses. If the composition of the feed is different than the composition of liquid or vapor that is already existent in the feed tray, then you are going to disturb the operation of the column. So, that mixing loss is avoided in a pre-fractionator system, and therefore, the total efficiency increases. Another design aspect, another design variable of columns is direct thermal coupling. I told you that how columns can be coupled in a sequence. Okay, vapor of one column condenses into reboiler of another column, but that again occurs, that heat exchange occurs in a heat exchanger which has limited efficiency. So, there is reduction in total efficiency of thermal total efficiency of heat integration. That particular aspect is avoided by direct thermal coupling of distillation columns. Now, what does that mean is that the vapor from one column will condense directly into the reboiler liquid of the another column. There will be no any kind of a heat exchanger as such. Direct thermal coupling, so vapor directly condensing into the liquid, and let us see how that feature occurs. Okay. Simple column should have a reboiler and a total condenser. However, material flow in the column can be used to provide some necessary heat transfer by direct contact, and this heat transfer is by direct contact is known as thermal coupling. Now, what I have shown here are the two possible sequences of thermal coupling. Direct coupling, which means that you have two columns and the vapor that is required by the first column is provided by the second column, while the reflux liquid that is required for the second column is provided by the first column. Direct coupling or side rectifier arrangement, that is called as the thermal coupling of a direct sequence. So, this is what you see on screen now is that particular arrangement. We have two columns and see how they are coupled. We eliminate the reboiler of the first column by condensing vapor of the second column in the liquid directly. The vapor is directly fed into the column, okay? And then the liquid that is coming from the first column is directly fed into the second column. Now, these kind of columns can be coupled as follows, that each column we divide in two parts, first column 1, 2, second column 3, 4, and then you can put the fourth section, that is the second section of the second column below 4, below 2, that is below the bottom section of the first column, and then you can have this kind of a sequence 1, 2, 4 and 3, and column 3 is a small column that takes vapor from the main column and returns liquid to the main column. So, that is thermally coupled direct sequence. This particular arrangement takes off B, the middle product, as the top product or the distillate product. So, this column 3 is known as a side rectifier. You can also have a thermal coupling of indirect sequence. Now, that is being shown on your screen. Column 1 and column 2, again column 1 divided in two parts 1, 2, column 2 divided in two parts 3, 4. Here you see that the reflux liquid required for the first column is given by the second column, while the vapor from the first column goes into the second column. Now, these columns can also be connected. The section 3, that is the top section of the second column, can be put above the top section of the first column. So, 3, 1, 2 is the coupling, and then you can see a short column which is known as a side stripper besides the main column. Now, the side stripper takes reflux liquid from the main column and then returns vapor to the main column, and here middle product B is taken off as a bottom product. So, this particular arrangement is called as a side stripper, because the middle product is taken off as a bottom product. In the previous case, the side rectifier, the middle product was taken up as a top product. It has been shown that both side stripper and side rectifier reduce the energy consumption, and this is a result of the reduced mixing loss as we have seen earlier in the first and main column. As with the first column of simple sequence, the peak in composition occurs with the middle product. However, in a thermal coupling, the advantage of the peak is taken by transferring the material to side rectifier or side stripper. Now, the question comes, as if these columns have so much of advantages, should they be always be used? But there are certain limitations. So, let us see the advantages and disadvantages of thermally coupled columns. Among possible configuration, the side stripper arrangement is common in petroleum industry. However, fully thermally coupled arrangements are not very attractive to designers. Now, why? There are reasons. If the heat integration of sequence is considered, it is observed that sequence with higher heat load, higher total heat load occurred simultaneously with more extreme levels of temperatures. Let us say you take up the mixture of hydrocarbons. If you see the total heat which is supplied at the reboiler, more or less same heat is recovered at the condenser. However, the temperature of that stream goes down. So, although the total amount of heat recovered is same, it is degraded in temperature. We are going to have a quantitative treatment of this in one of the tutorials. We shall determine how we can determine the temperature difference between the distillate and bottoms by using the feed conditions and the relative volatility, all those factors. Now, if you have higher heat load and more extreme levels of temperature, then the sequence is not suitable for heat integration. So, in the conventional arrangement, there is freedom to choose the pressure of the two columns independently. Thus, the temperature of the two condensers and reboilers can be also varied independently. Suppose you have to couple two columns, okay. Then as I said, you vary the pressure, increase the vapor condensing temperature in one case, reduce the reboiler temperature and let vapor condense into reboiler of another column and then heat integrate. But when you have a thermally coupled sequence, that particular freedom is gone. Okay. So, you cannot have temperatures of the two condensers and reboiler varied independently. So, that is a major discrepancy. Then smaller heat duties work to the benefit of heat integration, but more wide temperature difference between condenser and temperature offsets this advantage. The higher vapor temperature at the top of the distillation column and lower liquid temperature at the bottom of the column makes heat integration feasible. So, that feature we have to see rather than thermal coupling. With thermal coupling, the energy consumption in a single column reduces, but the column becomes more misfit for total integration, because to do all this thermal coupling, your temperatures are fixed. So, you cannot vary the pressures independently. So, let us say you have another process stream is sufficiently surplus heat, which is at slightly higher temperature. So, let us say you want to reduce the pressure of your column, so that your reboiler can be coupled with that stream. No, that freedom is gone when you have a thermally coupled column. Therefore, it is often recommended that the thermal coupling be considered only when full heat integration context is done, okay, has been understood. So, consider thermal coupling only when you have the complete data, we have complete heat integration. As a first pass through the design or at initial levels, thermal coupling should not be considered, because it is going to severely cut down your degrees of freedom in the design, and rather simple design columns should be used until the first overall design is established. Okay. So, this factor we need to note before designing the distillation columns. In the next lecture, we shall see some quantitative treatment. We shall see how to determine the height of the column, how to determine the diameter of the column, what are the different types of distillation columns that are available,